Hello there, this is your average student with another series called Control Systems Lectures. These are a series of advanced control systems, as this channel will concentrate on advanced topics relating to master's program. This is an introduction to a series of videos that is about to come, so hit the subscribe button and bell icon for more videos. Before we begin, I want to give an idea on what the first few dozen videos might be about. We will learn the history of control systems, introduction. We will learn how to mathematically model systems using basic examples. We will design feedback controllers and learn about frequency domain. PID will be taught in this series. Control implementation for analog and digital control will also be covered. So it's a huge field and it's just the beginning. So hope you are with me throughout. Okay, let's begin. So what is a control system? By definition, they are principles we apply, generally bounded by mathematical models, in order to get a desired outcome from a system. Well, a control system has multitude of uses in the real world. Most common example people think of is self-driving vehicles. How a car has the ability to maintain trajectory by any means necessary. So how does it do it? What it usually does is it will use what's known as feedback systems to maintain its trajectory. Here the feedback could be condition of the road, as it's made out of smooth or wet surface, would be more controlled, manageable speed, as opposed to climbing a steep hill or maybe hitting the highway with no traffic in sight. But this is just a small area of control algorithms. Apart from the pure mechanical movements, even software can have these principles. Maybe the car has the ability to identify its surrounding to have a better autopilot system. By differentiating text, color, or even people will help the controller make better decisions. And the feedback here could be the exposure or lighting that the camera adjusts to depending on the condition of the environment, so it can fine-tune its image processing algorithm. So are feedback controllers complicated by nature? Of course not. It doesn't have to be. I will bring some historical examples to prove it. In 250 BC, before Christ, there was a feedback mechanic system for time management. As you can see, the drawing on the left shows a controller that has the multiple mechanical parts controlled and governed by water as an input. So how does this work? As the water flows, the level increases, which then activates this ratchet and pinion mechanism, which will then in turn move the clock. Let's take the equation for this. Height of the water level is the volume divided by cross-sectional area. Volume here is flow rate into time. But flow rate over area should be a constant here to have consistent time regulation, or else you will have a clock that will move differently every time we use this machine. Hence, we will get the equation where height is proportional to time. But what is the feedback here? The feedback should be a system that maintains flow rate, because height will not change automatically unless the whole thing morphs into a different machine altogether, like some kind of futuristic sci-fi tech. So how do we maintain flow rate using traditional technology available back then? Here is an example we used. This is the common flow rate feedback system which we even use today for our flush bowls in toilets. The water is maintained using float valves. Maybe. Some other examples are liquid regulators, other examples for mechanical control systems back in the day. As the oil here is burnt, it leaves a gap for the air to rise up due to the pressure difference and push the oil in the second reservoir to come down and help maintain the flame. Another liquid regulator would be wine tank or a wine bottle, automated wine bottle. As you leave an empty glass, a series of hinges will activate to open a valve at some point, forcing the wine to go through. Once the glass is full, the hinges will then activate again due to the weight of the glass, which will then close the valve. It's like an automated bartender in the ancient times. Probably would be entertaining, especially if you are drunk. Finally, we have the modern flywheel or flywheel governor. Very interesting device. This is a mechanical system that ensures certain speed is maintained in the engine. If you force the engine beyond its speed limit by increasing the power, the RPM generated will be channeled to the flywheel attached to the engine. This will then pull a hinge because the linkage starts to lower down as the flywheel is causing centrifugal force. Hence, the steam valve will then close on the other end, which will force the engine to slow down and maintain speed. Very interesting device. I suggest you to look this up on YouTube. There's enough videos showing a visual representation of how a flywheel works. There is something you notice from all of these discussions. They are mechanically coupled feedback loops. Why is this important? Because we don't do this anymore. We don't find mechanical feedback systems in the modern engineering applications. Or a better way to put it, you rarely do due to the existence of sensors. Sensors are more reliable and precise with the feedback. We don't need to couple with mechanical hinges or flywheels, hence making it smaller and reliable. And of course more robust because less moving parts, and definitely scalable. But it's nice to see this as an inspiration, so we know how far we have come since we first started. This was a short intro, and I will try my best to upload new videos every week or every other week. So do subscribe and help me out. I will see you in the next video.